Hello and welcome back to the MCAT grind. We have General Chem Chapter 3, Bonding. So bonding takes quite a bit of percentage, but mostly because you will see questions simply asking you whether a bond enacting in this formula is stronger than another. Those are very common forms of discrete questions. In passage question types, you may come across this newly discovered synthesized compounds and be asked whether the double bond or the triple bond exerts like a shorter bond length than a single bond, and the answer to that is yes, because the stronger bond it is, the shorter the distance between them. However, we will need to go through all of the topics inside bonding. So that goes from octet rule, where most atoms strive to complete their shell. Think about trying to become a noble gas, and the non-metals will want to gain electron, whereas the metals will want to lose an electron. So if you have the first shell, has a shell of 2 electrons, so that's hydrogen and helium, as well as lithium. They'll want to get the 2 electrons into like the first shell. So for lithium, you want to lose that 1 extra from the outermost shell and jump to just having 2 electrons in the outermost shell. Okay. Typically for others, though, oxygen has 6 electrons in the outermost shell, so you want to get 8 electrons in a valence for that complete second shell. Next we have covalent bond, which is bond between 2 non-metals, and they share the electrons either equally or unequally. You could have a non-polar covalent bond, which if they're similar in electronegativity, they pull the electrons equally as hard. However, if one, let's say, is carbon and one is oxygen, oxygen obviously has a little bit more electron and it exerts a stronger pull on the electrons because it's more electronegative. On the table, remember from our tables of trends, the higher up you go and the more right, the more electronegative a atom is. So we have polar covalent as well, and also the last one is coordinate covalent, where one atom donates all of the electrons to be shared in that covalent bond. So for instance, if you have a boron that's attached to 3 fluorides, and you have that covalent bond between them, the boron is just giving that 1 electron to be giving it to be done in the bonds themselves. And the fluorides compounds, they all give 1 each as well to share in that bond together, so they're sharing that bond. However, if that boron is bonded to another, let's say oxygen, and that oxygen shares that 2 electrons with boron, then that will complete the boron shell, but those 2 electrons is being donated completely by oxygen, the oxygen atom. So that's a coordinate covalent because oxygen donates all of that 2 electrons, and none of that was given by boron to share. Alright, now we have a way to look at how to draw covalent bonds. Initially, you want to count the number of valence electrons it has, and that simply can be said by the number on periodic table. Hydrogen has 1 because number 1. Carbon has 4 valence electrons, and nitrogen has 5. You can simply just subtract the number of electrons in its previous shell and to get the outermost valence electron number. Then what you want to do is distribute it so that they'll satisfy the octet rule, in which a slash is meaning they're sharing covalent bond, and in that covalent bond there's 2 electrons. So the 2 electrons in here, hydrogen completes it, very nice. Carbon has 1, 2, 3, 4 covalent bonds, and they'll contain 2 each. 4 times 2 equals 8, so that's 8 and satisfies the octet rule. Nitrogen has 1, 2, 3 covalent bonds, that's 6 electrons altogether, plus 2 more free non-bonded electrons, so that's 8 altogether. So that satisfies the bonding rules. Note that we also have nitrogen on the outermost side because that is better because electronegativity suits that the slightly positive H and the inner part carbon relative to the outside, which is nitrogen, is more which is more electronegative, is pushed to the outermost sides. Alright, we have 4 more charges, which tells us the relative charge of that atom if all the electrons are shared equally. So we have the valence electrons in the atom originally. So nitrogen originally has 5 electrons. So we want to minus 1, 2, 3 bonds and minus a 2 electrons bond. So its net 0. Its formal charge is 0. Carbon has originally 1, 2, 3, 4, minus 4, and that is a 0 formal charge. That makes sense because it did not change in charge or attraction because no electrons was newly gained or lost. However, if we take away one of these electrons here, it will become a radical, and it will be 5 minus 1, 2, 3, 4, and that will be a positive 1 formal charge for nitrogen. To determine the strength of the forces, we have these. We have hydrogen bond, dipole-dipole, and dispersion forces from strongest to weakest. The strongest type of intermolecular force, hydrogen bond, is exerted by when hydrogen does a weak interaction with either oxygen, nitrogen, or fluorine. Because they're strongly electronegative and hydrogen is really electropositive, they would experience an interaction introducing hydrogen bond to it. You may find hydrogen bond very common as the solution to questions asking what is the secondary structure for amino acids and peptides chains being made. Well, it is the alpha helix as well as the beta pleated sheets, and they're folded from the interaction of hydrogen bonds between the first and the fourth atoms or amino acids with each other, making either a coil or a pleated sheet shape. Dipole-dipole is the next intermolecular forces, and just like hydrogen bond, it exerted by weakly influence from the electropositive and electronegative side of atoms. However, it's not very electronegative atoms participating. So you have chlorine, maybe you have bromine. They're not as electronegative as oxygen, nitrogen, and fluorine, so they're just called dipole-dipole. Dispersion forces, or London dispersion forces, are momentarily repositionings of the electrons slightly towards more one side at any given time. So you have non-polar covalent bonds all the time, and they should, in theory, exert a net neutral charge. So F2, for example, O2, they would have supposedly net 0 charge, right? However, at some point in times, there may be electrons that are closer to one side than another, so that allows them to exert some kind of pull towards one another due to unequal distributions within the compound. So you could have chlorine, CO2, that may interact with another CO2 due to very weakly momentarily in time. Now, to base on how a molecular structure is positioned, we have to follow the Vesper theory, which states that the compound rearranges itself into the least energy extensive state, or the most comfortable state. Think about sitting down on the sofa. You don't want to be sitting upright and remain there, right? You want to kind of relax, lie down, and sink back to experience the least amount of energy, right? Relax. So if you have 2 excess electron clouds from a central atom, it will be a linear. Well, in the case of H2O, since there's a positive side and a negative side because of a highly electronegative oxygen, it's slightly more bent instead. Alright? That's what happens when there's an electronegative atom more towards the middle. Trigonal planar, it's the same thing. They all try to equally distribute against another, but if one of them is electropositive and others are also electropositive and one's electronegative, they'll probably bend towards the electronegative side and away from each other for the electropositive side. Tetrahedral is equally 109 degrees, 109.5 degrees spatially across from each other. And again, if there are dipoles within the structure, then there's going to be more bent either towards or from, depending on the charges. Trigonobipyramidal is just boop, 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 1, 2, 3, and up and down, like a bipyramid. Octahedral is same thing as trigonobipyramidal. You have the 4 across the midline, and you have 1 going up, 1 going down. And these are in respect to the different types of atoms and structures you may see. Questions you may be asked would be, what would be the general molecular structure for a given silicon, fluoride, 6-fluoride, right? And now if you have 6 electron clouds, you can remember that, okay, well, that's octahedral, because 1, 2, 3, 4, and then 5, 6 going up and down. Don't get tripped up for the octa part. Alright, that's about it.